problem that we just looked at was taking a linear function and determining the slope of the tangent line, which is pretty easy because the slope of the tangent line is itself the slope of the linear function. Now, here we're going to take a look at a quadratic function, so a general quadratic function to be precise. So let's say we've got some function f of x, and that's equal to some ax squared plus bx plus c. So we know that this is, what a quadratic function would look like. And we're going to find the derivative at some specific x sub naught value. So what this is going to find is it's going to find the slope of the tangent line at x sub naught. Okay, so it's pretty easy to do. Basically, it's just all algebra here. So we're going to use our definition of the derivative, our definition of f prime at x0. Well, I'm going to write it like this so that you get used to seeing it. F prime of something is going to be equal to f at that same something plus delta x minus f at that something all over delta x, with the restriction here that delta x is going to become really small. Okay, next chapter or next section we're going to talk about the actual definition for the limit, and we'll put a little bit more rigor to this. But for now, this is good. So we want to find it at x sub naught. So we're going to plug in x sub naught. This is just, we can find it at, so f prime at x naught. So what we're finding, we can find it at a, or we can find it at d, or we could find it at smiley face if we want to. It doesn't matter. Okay, it's completely irrelevant what this variable is. So this right here is going to give me this. Okay. So now we need to actually plug in x sub naught plus delta x into the original function. So that's going to be a times x naught plus delta x squared plus b times x naught plus delta x plus c. That's this first guy right here. And then we need to subtract off f at x naught. I'm getting a little tight over here, so I'm going to recopy this down here. Excuse me. So that's, in fact, you know what? Let me use a different color here. This guy right here that I wrote is this guy right here. Now we're going to subtract off this guy. So that's going to be a x naught squared plus b x naught plus c. Why? Because this right here is f at x naught. We're plugging in x naught into it. And that's all over delta x. So we'll go ahead and we'll distribute this guy out. So it's going to be a times x naught squared plus 2 x naught delta x plus delta x squared plus b x naught plus, oops, I'm actually going to multiply that in. It doesn't really matter, but let's just do it anyway. B x naught plus b delta x plus c minus a x naught squared plus b x naught plus c, but we're subtracting all those, right? So let's switch this to negative and that to negative. Okay, because we have to subtract out each piece. All over delta x. So what? So now we've got to go ahead and multiply this guy in. So this is going to be a x naught squared plus 2a x naught delta x plus a times delta x squared plus b x naught plus b delta x plus c minus a x naught squared minus b x naught minus c. That's all over delta x. It's a lot of work, right? But we just, as long as we're consistent with our algebra and we're making sure our variable's in the right spot, we're good. Okay, so now what cancels? Well, the ax naught and the negative ax naught squared, those cancel. The bx naught and the negative bx naught cancel, and the positive c and the negative c cancel. So we're left with only things with a delta x in them. And so I'm going to factor out the delta x out of the top, and I'm left with the following. 2a x naught plus a times delta x plus b all over delta x. Now, the idea is we're letting delta x get really close to 0, but not be equal to 0, so we can cancel these guys out, and we can say that this is equivalent to 2a x naught plus a delta x plus b. As delta x gets really close to 0, 2a x naught plus a delta x plus b goes to just 2a x naught plus b. This term right here is going to become incredibly small so that it really is irrelevant anymore. I mean, it's like if you had $1 million and someone gave you a penny, you wouldn't care because the penny doesn't matter. It's so insignificant. That's what that piece right there is. Okay, so our final answer is this. Well, so what? What does that even mean? What that says is, let's say you got a function like this. F of x equals 3x squared plus 7x minus 6. And you want to know what is the slope of the tangent line at 4. Well, in general, the slope of the tangent line is equal to 2 times the a value times the x naught value plus the b value. So what do we have here? Well, our a value is 3. Our b value is 7. Notice that c is not even a part of this, and there's a reason for that. Okay, the reason c is not a part of this guy over here is because all c does is moves the graph up and down. It doesn't change the slope. So if you think about a graph like this and you look at the slope of the tangent line, if you move that graph up or down, that tangent line is still going to have the same slope. It doesn't matter whether you move it up or down. That's why c doesn't matter in here. And our x naught, guys, is 4. So what I can tell you is, for this equation right here, the slope of the tangent line at x equals 4 is going to be given by 2 times a times x naught plus b, which is 2 times 3, which is 6 times 4 is 24, plus 7 is 31. So the slope of the tangent line for this particular function at an x value of 4 is 31. So here's what I mean. This function, I don't know exactly what it looks like around the origin, but I can tell you that at 4, when you go up, okay, and you look at the tangent line at 4, this guy has a slope of 31. That's what I can tell you. Okay, and that's just based off of using this general form.